Hello, this is the last video in Light as a Particle, number 8, Wave-Particle Duality. So, if we summarized all the previous videos, not just the light as a particle but also the light as a wave, we can see that there's evidence for light as a wave and there's evidence for light as a particle. Double slit interference, diffraction, thin films, electromagnetic waves, polarization, and the Doppler effect, which is evidence of waves, whereas particles, we've discussed black body radiation, photoelectric effect, X-ray production, and Compton scattering. So, what is light then? Is it a particle or is it a wave? Well, earlier before the 20th century, physicists had worked out, looking at all the evidences like reflection, refraction, interference, diffraction, polarization, they reckon, well, light must be a wave. But then, as we entered the 20th century and then now into the 21st century, things were starting to happen that could only be explained in terms of particles. Such as, or could be explained in terms of particles, such as reflection could be explained in terms of a particle, refraction could be explained in terms of particles, but interference still couldn't be, diffraction still couldn't be, polarization couldn't be. These are definite wave characteristics, whereas the photoelectric effect can't be explained by wave characteristics, but can only be explained by particle properties of light. So light is both. It's both a wave and a particle, and in terms of modern physics, it depends on the situation that it is in that determines whether it behaves like a wave or a particle. Pretty confusing, but that is the duality of light. And we get hung up on it because as humans we like to rationalize things and imagine things and conceptualize things, and it's very hard for us to conceptualize the idea that something can have two properties at the same time and only determine when to have or display that property depending on the situation. Much like we get confused about the whole idea of, in Young's double slit, if we fire single photons, the photons can actually go through both slits at the same time. That really throws most people, but once we get an understanding of what we're talking about in terms of physics and how it's actually beyond our perception, we can start understanding it, that that's actually what's happening, and we just have to accept it. And so the duality, or the wave-particle duality of light, is something that has puzzled people for a long time. Now, we also need to mention the de Broglie wavelength, named after Louis Victor de Broglie, who was around in 1892 to 1987, and that's what he looked like. And he suggested that all matter could exhibit wave-like characteristics. Now that was a bit of a revolution at the time because people had been studying waves and the wave properties of things for many years, but they had drawn the line and said, well, some things just don't have wave properties. And what de Broglie was saying was that everything has wave-like properties, and that fits into the quantum theory of matter. And he specifically was saying that electrons in orbit, which are particles, and they're just undergoing, if we simplify it down, they're just undergoing circular motion, but that wasn't a good description of what they were actually doing. And so the better description was to consider electrons in orbit as actually having a standing wave motion, and that was a result of their momentum. So we've thrown all these things around, and we have to just reshape our whole understanding of how atoms, how electrons, how matter works. And because of this standing wave motion, only certain orbits were available for the electrons to be in, and that tied in well with Bohr's work on energy levels. And there we are, and Bohr's quantum orbitals, in which there are only, if you any element only has certain energy levels at which the electrons can sit. And we're actually going to do this in the next topic, atomic physics, but we've been mentioning it a bit because it all ties in with our understanding, or our very brief brush with modern physics. And so this is what an orbital will look like. Well, this would be an unsuccessful orbital, in that the electron would have a wave pattern, and this would be the standing wave pattern, but it needs to be an integer. The number of wavelengths has to be a whole number. It can't be a fraction, otherwise it wouldn't be a standing wave. And so this is why only certain orbitals are available for different atoms, and it's an interplay between what's in the nucleus and the forces and the electric and magnetic fields, and where the electron can actually be. So every element has its own discrete pattern of energy levels for its electrons. And that's what de Broglie came up with. And he proposed that the wavelength of a particle, so every particle has a wavelength, and that's related to its momentum, p, according to the following equation. So the momentum of a photon is p equals h on lambda, the wavelength, and the momentum of a particle is p equals mv, which we've done before. Put the two together and we get this, and therefore we get the de Broglie wavelength, which is this. And so we can see that all matter has momentum and all matter has a wavelength. Right, now the wave properties of matter are very difficult to observe. That's half the problem. So let's do an example here. Let's calculate the de Broglie wavelength of a mass of 100 grams, 0.1 of a kilogram, moving at 10 meters per second. Put the numbers in, and you can see that it's a very small number, minus 10 to the power of minus 34 meters, which is much smaller than the wavelength of even the most energetic gamma ray or cosmic ray. And in practice, it's impossible to find objects small enough to actually measure that wavelength, but it's known to exist. I'm having trouble. And so that pretty much wraps up everything we need to know about light as a wave, light as a particle, and light's wave-particle duality. And so in the next topic, or the next unit, we'll actually look at atomic physics, and we'll touch on some of the things that we've discussed here in a little bit more detail. Bye.